All right. Now, let's talk about safety. 3 situations that we need to be aware of, planning for, having in the back of our minds, how would we respond, how would we react? 3 things that deal with safety. Can anyone think of any one of them? Say again? Fire. Okay? Something happens within the building. Okay? Let's start with what I would consider one of the worst case conditions. Let's say that we see smoke start billowing out of the ventilation gear. Okay? So we're the first to see this. Or let's say my computer explodes. I hope that doesn't happen and sets the desk on fire. Okay? We're the first to know about it. What do we do? Say again? Fire alarm, for sure, but fire extinguisher is not bad either. Okay? Where is the closest fire alarm? Nowhere real close. Okay? Here we are. For a minute. This is a diagram of the second floor, or mostly the second floor. They sort of have it swirly, but it's okay. Starts down there, there's my office right there. Comes up this half flight of stairs, there's a full flight over here, half flight here. Comes up, this is all second floor. We're in this classroom right here on the corner. Long hallway going that way, and then you take a left and then another. It forms a horseshoe here. This is the oldest part of the building. Okay? This part was built before they had in the code the fire alarms. There is nowhere on this old hallway here, any of the hallway you see going out this door and this part here, that has a fire alarm. Nowhere. So don't go wandering the hall looking for it here. Where do you find it? Okay? After these, actually, this was 2 parts of the building, this part and that part. Those are both way before the town. This part over here is actually first floor. Why they have it on the second floor diagram, I don't know. This is half a flight down from these rooms. See, this goes into this thing, this goes into that area, this goes into that area. These are all second floor. This is first floor. This is second floor. That part may have fire extinguishers, but that's a long way from. Fire alarms. You got me doing it. Okay? But don't go there. The closest place is go out the door here, hang a left, go down this hall, down this half flight of stairs, go to this corridor here, just past the restrooms. That leads you right into the financial services office, right? That's the newest part of the building. Since I've been here, it's been built, okay? When you go there, I think immediately on your left and not far on the right, you'll find fire alarms. So go that way. So at least one person, maybe 2, go down to pull the fire alarm. So that's one good thing to do. But then you snuck out one other word, by mistake, I think you said, fire extinguisher. Where's the closest fire extinguisher? Right on the wall here, okay? When I said, so I left the door open. When I'm standing here, it's 5 feet from where I'm standing. Right there is the fire extinguisher. So I'll probably have to get that when y'all go to it, unless one of you like to break the glass and you can get the fire extinguisher. But I'll deal with it. Now, we can't do anything for smoke coming out of there. We can't get into that room. It's usually locked. Okay? But if my computer exploded and set the desk on fire and my papers, that fire extinguisher is fine there. Okay? There are 3 types of fires. There's more than that, but 3 that we'd be most likely to have. Paper or wood, that fire extinguisher, fine for that. Electrical, that would be involved with this, that fire extinguisher is good for that. Grease fire, that might be what's coming out of that room, that fire extinguisher is okay. Water would be okay on this, paper or wood. Would not be good on electrical because water conducts electricity and you could wind up getting shocked, electrocuted. And water is not good on grease fires because it actually spreads it, because water and grease don't mix and you actually spread the fire. But that is not a water extinguisher. That is, I think, compressed carbon dioxide, which will work on all 3 fires. So we've done two things so far. Someone's gone to pull the fire alarm. Someone's gotten the fire extinguisher, if it was in this room. Anything else we should do? Say again? Leave is certainly one, but either on the way or before we leave, one more thing we ought to do. Yes, you need to call somebody. Now, if you have a cell phone, I think it's a great idea to have programmed into your cell phone the Lawson State Police number. Fantastic idea to have. So if something like this, you dial them and let them know first. But if you don't have them in your phone, don't know the number, 911 is the next best. Okay? And, as you say, we leave. Now, where do we go? Okay? We go out the door here, take a left, go down this half flight of stairs, take an immediate left, go down one more complete flight, and then get out of the building. Okay? Now, this diagram here, this is not the best diagram. This is the interstate back here. That's on that side of the building. Okay? Here is Bessemer Superhighway. That's it right here. We would be coming out of this door right down here. There's our classroom. We would come out of this door. And frankly, I think the grassy area out here, at least 75 feet away from the building, would be good. But they tell us to go down to the parking lot. So we go down to the parking lot. Okay? The one down there between this building and Ethel Hall. Okay? Now, does that mean you're going to the parking lot? Why don't we get in our car and go? Oh, the building's on fire. No more classes today. Do we leave? No, don't even think about it. Because, let's just get the picture straight again. Now, let's back off a little bit. If you hear the fire alarm goes off, not from this room, okay, then all we got to do is leave. So that's the thing we do. If the alarm goes off, someone knows about it, security knows about it, everybody knows about it, you proceed out of the building. Only if it's here do we do these other things. But if we are doing those other things, then we regather, regroup as a class down there, because I'll be taking my rule book with me. And once we get there, and by the way, let me back off on this one too. You all look pretty healthy now, okay? Way to go. But what if you go skiing one weekend and break a leg? So you're either on crutches or in a wheelchair or something like that. Then I'm going to stay behind and make sure you get out of the building safely. And if it's more than I can handle, I might call on one of you strong, able-bodied people to help me get that person out, okay? So we may not get down there in the parking lot at the same time, especially if one person did the fire alarm and one person was calling and one did the fire extinguisher. We're not going to get down there at the same time. But even if it's leaving together, if someone is a little incapacitated, I may be the last one there because I'm getting that person out. So you'll get me down there first. You don't get in a car and leave. Because when I get down there, I'm going to call the roll. And I've got to account for everybody. If I can't account for everybody, somebody, me, or a fire emergency personnel, has got to go into the burning building trying to find you. Okay? Risking his or her or my life or health trying to find you when you wandered off to visit friends, drive home, stuff like that. Don't do it. Stay together at least until we get a good roll and we hear from the people. If they say, look, school will be dismissed, you're free to leave. Or, hey, hang around, we're going to redesignate classes in different buildings. Or something like that. Wait until we find out. Okay? Certainly until I've accounted for everybody so we don't risk anyone else. So there's fire. Check. 2 other safety issues. What would they be? That was inside the building. What about outside the building? Weather. And this is spring. Now, by the end of the term, we could eat. Oh, by the way, let me back up. Time out again on the fire. Last term, in the fall, we had, as far as I can recall, the first fire drill that we had since we merged with Lawson. Back when we were at Western State Technical College, I can remember maybe 1 or 2, then. But we had the first one I can recall since the mergers. That was 05 or something like that. So they say we're going to start having these each term. So sometime this term we will have a fire drill. Okay? We will proceed out of the building just like I said. The one we had back in the fall, they did something that I thought was rather poor. They directed everybody to go out the same door, which is not what you do in a fire. You go out the closest section. So I refused to do it. I told them, I emailed them when they said that. I said, no, you don't practice wrong behavior. You do the right behavior. If you want us in the parking lot there, yes, we'll meet there. But you should go out the door that you're supposed to go. You practice it so you'll know what to do in case of an emergency. So what I did with my class, and it got people upset, but I told them I was going to do it. We went out the door we were supposed to, and then we went around to the back parking lot, which we weren't supposed to. We got on the outside. I said, now, if this were a real fire, that's where we'd be. They want to talk with us, so we're going here. We wouldn't do this if it were not a drill. Okay? So I made a point of that, and I think they understood later that that was what you're supposed to do. So they said, we'll go to the right places this time. Well, I'll wait till I see it to believe it, but hopefully we will. Okay. So let's go to weather. Well, we know if there's a weather emergency, you'll hear the alarm outside. Okay? You'll hear it before I will because I'm already here. Okay? If you hear that alarm go off and I haven't responded to it, get my attention. What do we do? Okay, you're right. We go low and interior. That's where we go here. Where is that for us here? You go out the door here, hang to the left, go down the half flight of stairs, hang to the left, go down the full flight, but rather than going out of the building, you go into the building. So down on the first floor, it looks a lot like this too. And so one of the best places to be, when you go down to the first floor here, you're near the lowest point in this building. Good place to be. Actually, these two restrooms here, actually, you only go to the male restroom. The restrooms are one of the safest places to be because the walls are closed and you got a lot of angles. That's where you have your strength on the walls and especially in the corners. That's where the greatest strength is. Okay? So, on the downside of that, if it's going to be a prolonged experience, you may not like spending the next hour or two in the restroom, okay? Especially if it is a weather emergency in the area, there's a really good chance the power will go off. So if the power does go off, then restrooms, again, probably not the favorite place to spend it. The advantage there is the hallway has emergency lighting, the restroom does not. But if the restrooms are full or you don't want to go to the restroom, right next to it, underneath this corridor here, is actually an office. That is the academic dean's office, and either Dr. Davis, Dr. Pruitt, and sometimes Dr. Briggs, though he's not academic dean, sometimes when they're on this campus, they use that office. Now, they're not here much. She tries to get here a couple days a week, doesn't always make it. It's not always the same 2 days. She used to shoot for Tuesday, Thursday. I don't know what she's shooting for now. But quite often that room's locked, so don't break in or anything. If someone's in there and wants you in or will invite you in, it would be a decent place to be because it's interior. Walls are close together. Next after that would be the hallway. The walls are further apart and there's no corners in the hallway. It's all straight line, but still the walls are safe. I remember hearing about a tornado that hit a school, I think it was Piedmont, but it may have been one of the other towns in Alabama. And there were a group of cheerleaders, I think it was after school, but the sports teams were practicing, the cheerleaders were practicing, and they stood on the wall of the gymnasium. And I can't remember, it seemed like they said that saved their lives. The roof collapsed. They were against the wall, so they were scared. They may have been injured, a few of them, but I think that saved their lives. If they'd have been in the middle, probably not. Okay? So the hallway is really the place they designed it for that has the emergency light. But you have the walls further apart and the corners aren't there. Okay, but if that's really crowded or stuffy or something like that, the next room down the way is room 160, which is developmental math classroom. I don't know if you know where that is, but that would be a decent place. Again, don't get in the middle of the room. Don't get where manual is there, but get near the wall, preferably near a corner. Okay, again, no emergency lighting there, but you have a little more room there. Then you go through the glass doors that go into the library area, and immediately to your right there is a computer room. Not a bad place. It's smaller than the classroom, the walls are closer, and if you can get in a corner against the wall, not bad. And by the way, let me say, the wall back here, that's against soil. So there's not a great probability that that wall's going to come down, because it's got really good reinforcement behind it. So that would be the preferred wall if you're going to be able to. The next room, past the computer room, is what I call the research room, or the something like that, has the globes and the atlases and those kinds of things. Not a bad space. It's maybe about the size of a little bit larger than the computer room, but it does have shelving, and the shelving can fall down, okay? But if you get in a good safe corner or this back wall, it's not bad. But don't go any further in the library, because any further in the library, you're in windows, exterior room. Don't go on this side of the hall, exterior. And the problem with that is during a tornado, straight line wind, severe thunderstorm, where there's a lot of wind, limbs can get broken off trees and come into the building. And if the limb doesn't get you, the glass could. Don't be in a room, an external room that has glasses. And even one without windows, still the wall can come in. So you don't want to be there. Lowest level, interior. And again, if one of you are injured or especially say in a wheelchair, okay? If I can get you down to the lift, now where's the wheelchair lift? We don't have any elevators in this. The only wheelchair lift available for here, and you would know if you're in the wheelchair, is that this stairwell way over here, about as far away as you can get from where we are in this classroom, and still be in the building. If we can get there before the power goes off, then we can get you downstairs, and then when we got you downstairs, I'll probably get you out into the parking lot here. Okay? Away from the building. I'm sorry. This is weather emergency. I'll get you to the lowest level, which is the first floor here, get you to the interior hallway, either one of these classrooms or hallway or this hallway, something there. I'll get you there, get you settled. I'll come back and find the rest of the class. I'll account it for you. Okay. Now, if you're on crutches or something like that, or if the power goes out and we've got to get you downstairs, either in the wheelchair or out of the wheelchair, I'll probably need some help. So one or both of the rest of you will be helping me get that person downstairs to safety. Okay, and don't go off and wander around and say, hey, I got to get home and let the dog out. No, you don't do that. The worst place to be in a weather emergency is in a vehicle on the road. Stay in the building. Don't say, hey, it's no more class today. This is a big tornado. Power's out. No, stay in the building. And also, don't wander off and visit with friends until I've made sure I have accounted for everybody. Otherwise, myself or someone else has to go up where the winds could be blowing limbs through the windows and try to find you. And let's not do that. Okay. That, I think, covers weather. Any kind. If that alarm goes off, that's what we have. What's the third? Active shooter. I never even used to think about this. But nowadays we have to. Now, I've only known of one community college where this has occurred, but it has occurred. So it's not likely, but we have to know what to do if we hear gunfire. Now, again, I'm hard of hearing. You probably would hear it before me. What do you do if you hear gunfire? Say again? Dial. Excellent. First thing, dial 911, preferably the campus police if you have them in your speed dial. But if you don't, dial 911. Explain to it what you hear. After that, we get as quiet as possible. Okay? What else do we do? Okay. I'm going to lock the door. And obviously, I don't keep the door locked because I want students to be able to come and go. Preferably come. Okay? How do we lock the door? Well, there's no buttons here to lock the door from the inside. What I have to physically do is go outside the room and lock it from the outside. Trimming hands, that kind of stuff. I'll do that. Don't pull the door closed on me. Let me get in. Then we'll pull the door closed. Okay? And then we stay very quiet and outside the vision of this window. Turn off the lights. We want him to think nobody's home. Room's locked. Nobody's in there. But we have another door here. Okay? Now, this door here can't be locked with buttons on the side. But don't do it. Lock that with buttons on the side. You lock it from here, but you don't lock it from the outside. So we get locked in, and he can come right in if he wants to. So you do not lock this door. Okay? This one has a deadbolt, but I don't have a key that operates this door. So there's nothing we can do with that. However, campus security, police, or whatever you call them, they think that's not a classroom. Okay? Obviously a classroom. Okay? It's not a computer room. Okay? But the vast majority of mornings, like right now, that door was locked from the outside. Out the other lock. I could get out, but I couldn't get in. So if that's the case, now what I usually do to keep people from interrupting my classes when I'm teaching, trying to get into that class, I go and open the door, which I just did. But in case of an active shooter, go and close that door. Whether it's locked or not, locked is great, not locked, still close the door. Turn off the light. We don't want them to think anyone's home. But if that's unlocked, especially, this door also has buttons on it. If I press that button, we can get out, but he can't get in easily. Okay? So this is the one we want. Okay? Now, the bad news here is the glass. So if that door's locked, that's our best thing. If it's not, close it, turn off the light, get in here, lock this door, so he can see in. So, what we do, close and lock the door. We close this door. We can't lock it, but now he can't see in here. So hopefully he thinks no one's home. And you won't break the glass to come in and look for him. Okay? And what we do is get back here. Once we got the door secured, the 911 call, we turn off the lights, get very quiet, get back here. He can fire through the window, break the window. It's going to be hard for him to reach in and open the door. He could shoot through the wood. Man, it'll lose a lot of force. It's hard to shoot through concrete block. Okay? So that's the safest place to be. We're out of sight. Doors locked. Lights off. Hopefully, he assumes the room's empty. Okay? That's what we do, and we stay like that until we're absolutely certain. Say security comes around, unlocks the door, they have the key, and tells us everything's safe. Okay? Hopefully, it's not going to happen, but in case it ever did, you need to know what to think to do. That's what we do. Any questions on safety? All right, sorry that took way too long. Okay, let's get started on math, please. Okay. We are recording, that's good. I just want to check something quickly. Man, this thing is so slow. I'm not sure it's operating, that's what I want to check. We are recording. Okay, I guess I can't tell. There we go. Yes, I think it is trying to push my the afternoon evening class. All right, what we have done so far with safety, you have to listen to today on YouTube to hear the safety. But you've been in my class before, you may have heard it before. Okay, but we are recording and just getting ready to start actual math now. Let me say this one also. All four of you are paid. I think you're the only four that are going to be in the class, as far as I know. Matt, who was here last time, dropped this one and added a different class, so he's not going to be back. But the four of you are paid, so hopefully no problem. What supposedly they did yesterday afternoon was remove all unpaid students from the classes unless they knew they were in progress, like waiting on financial aid or something like that. So if you have any friends, know of anyone who may have been removed from a class, tell them to get in touch with the business office and our financial services, somebody, and let them know what the plans are. Waiting on the scholarship, waiting on financial aid, waiting on the tuition management, whatever the situation, or just waiting for the check and going to pay as soon as you can. I think they'll put everybody back in, but it's just such a pain in the neck for them to take them out, put them in and stuff, because every time they do that, I have to re-enter all the attendance, okay? And it's nuts. It's really crazy, but that's what they've chosen to do. All right. Now, I think I mentioned to you before, this book has no PowerPoint. So I have to do everything on the screen, okay? And just about everything we'll do, if it'll open, it's a huge PowerPoint file, 2 pages or 3 pages, that's all. And yet it's real slow opening. In fact, it's not opening. So let me try it again. Okay, now it's trying again, and not. Okay, it's trying again. I mean, it's 3 empty pages, that's all it is. Sorry about that. Here it comes. I really dislike Microsoft products. Just sorry. Okay. Now, things we're not going to do in the text. I think I mentioned this before. Introduction to systems of linear equations. You should know systems of linear equations. You've gotten this far in math. Surely you know. If there's anything you've forgotten or fuzzy on, ask me. I'll be glad to go over it. Okay? However, we are going to do something in 1.1 because they come up with a definition here. Well, not a definition. Goodness, we're still waiting for that to get there. It's I guess, a description. Okay, first, you tell me, what is it that makes a linear equation a linear equation? What makes a linear equation a linear equation? What is the requirement? Equation means it has to have a equal sign, okay? Got to have an equal sign. Something on one side, something on the other side. Now, what makes it a linear equation? That deals with what are those somethings, okay? What would be involved in those somethings that are on either side of a linear equation? What you normally have on either side of an equation, equal sign. Have numbers, variables, and operations, okay? Those 3 things, that's about all you have on either side of an equal sign, one side or the other, okay? Sometimes it will just be one thing, a number, or one thing, a variable, or some combination, okay? So what is it about the numbers, the variables, or the operations that makes it a linear equation? Doesn't matter about the numbers. They can be anything. The variables, okay? Now, if it's something you can graph, obviously it has 2 variables. Horizontal, vertical, okay? X, Y, RT, whatever it happens to be, 2 variables. What is going to make that a linear equation if you graph it? What's the first 4 letters in linear? Line, okay. It graphs to be a straight line, okay? Now, what is it about the equation that is going to let you know before you graphed it that you can look at it and say, yes, that's going to be a linear equation? Any ideas? Very good. Each and every variable is only to the first power. Only to the first power. And basically, we're going to be working with only linear equations in this course. That's why they call it elementary linear algebra. We're working with linear equations. Okay. Feel like a dentist here pulling teeth. Okay. Now, so every equation is going to be graphed as a straight line. It could be a positive slope, a negative slope, a zero slope. What would that one be? Infinite slope. In other words, you might say no slope. The better way to say undefined slope. Because if you say no slope, you might assume that's zero slope. That's zero slope. This is an undefined slope or an infinite slope. Okay? So that's what your choices are when you have linear equations. Now, a system of linear equations, that means you got two or more equations. Okay? Now, let's say you have two equations, two variables, so you got two straight lines. They're linear equations. Tell me three possible situations if you graph them both on the same graph. What would they produce? So you have one equation that graphs like this, another equation that graphs like this. What do they have in common? A single point. Wherever those two lines intersect, that is the solution for that system of equations. Now, you could have something else. What's another scenario you could have? Here's that first equation. The second one is on the same line. In that case, we say they are equivalent equations. In other words, they are dependent equations. One of them depends on the other. One's a multiple of the other, but they graph as the same line. Okay? In that case, you have an infinite number of solutions, because every point on this one is also a point on that. Okay? One other situation you could have. What would that be? Say again? Parallel. Here's the first one. There's the second one. What do you have in common? Absolutely nothing. There are no solutions to that, because these two lines, if they're parallel, never cross. Now, if they're parallel, what does that tell you? How can you look at that equation you first have and tell whether it's parallel or not? You might have to do a little manipulation to it. What manipulation would you do? Yes, get it in slope-intercept form. In other words, how do you do that? Solve for the dependent variable. Quite often y, but whatever plots on the vertical axis, solve for that variable and see what you get. Okay? If you solve for that, you're going to have y, or whatever that variable is equal to some number times x. Remember, they're both to the first power. Okay? Plus some other number. It always is going to come out something like that. Okay? Now, those numbers, these are variables, y and x. This number that's the coefficient of x, what do we call that? Slope. That's the slope. Y is equal to mx plus b. That's the m. What do we call this number that's added to or subtracted from that mx? The what? B. Okay, we call it b, but what is that? It's a y what? Intercept. You're exactly right. If you get that linear equation in what they call slope-intercept form, you know what the slope is. You also know what the y-intercept is. So, if you get both of your equations in slope-intercept form, which is doable, and if they have the same slopes, they are going in the same direction. If they have different y-intercepts with the same slope, they have no solutions. They're parallel, never have a point of intersection. If they have same slope and same y-intercept, then they're on top of each other. Then you have an infinite number of solutions. They're dependent equations. And if they have different slopes, it doesn't matter what the y-intercept is. If they have different slopes, they got to intersect one place and one place only. Two straight lines can only cross in one place. If they have different slopes, they're going to cross somewhere. Maybe up there, down there, way off scale, but they'll cross somewhere if they have different slopes. Even if the slopes are very, very similar, not quite the same, then somewhere up there they're going to intersect. one and only one solution. So that's what we expect from a system of linear equations. All right, that was sort of covered on the bottom of page 5 if you have your book in section 1.1. Then they talk about solving a system of linear equations. Okay? And, all right. So far we've talked about straight lines, right? Two equations with two variables, system of equations. But guess what? You can have linear equations with 3 variables, 16 variables, 85 variables, any number of variables, as long as none of those variables has a coefficient other than 1. Other than 1. You don't have any fractional exponents. You don't have any, did I say coefficient? I meant exponents. Exponents. You can't have fractional. You can't have negative exponents. You can't have exponents greater than 1. 1.3, that won't work. It has to be 1 and 1 only. Positive 1 is your only allowed exponent. Okay? So, what we do, there's a technique, and there's a series of operations we do that you produce equivalent systems. Okay? And here are those 3 operations. Okay? This is the top of page 7. And by the way, in the margin on page 7, you'll see a very handsome character there named Carl Friedrich Gauss. Boy, what a mind he had. He was a German mathematician, physicist, scientist. He did a lot of things. He's recognized with Newton and Archimedes as one of the 3 greatest mathematicians in history. There are so many things he did, not just in math, but in physics too. By the way, Archimedes, I don't know if you would credit him with, some things in physics, but certainly engineering. He was a way ahead of his time engineer and physicist, but certainly mathematician. Newton, same thing, physicist par excellence, but also a fantastic mathematician. And Gauss is rated right up with them, okay? He used the form of what is now known as, and that's what we're going to talk about, equivalent systems, okay? He came up with this, and we call this Gauss elimination, okay? Later, we're going to hyphenate that with another guy named Jordan, take it one more step. But here are the operations that you do on linear equations. Why am I spending time on linear equations? We should be in matrices. That's what the course is about. Well, guess what? We use these same operations there. So here are the operations that produce equivalent systems. Each of these, when you operate on a system of linear equations, produces what we call an equivalent system. The first one of these, whoops, wait. Okay, the first one of these is if you have a system of equations, okay, 15 equations with 13 unknowns, system of equations. You can have 13 equations with 15 unknowns. Any number of equations, any number of unknowns. You have more than one equation, though. One thing you can always do is interchange the 2 equations. Okay? Later we'll be talking about other things. Because guess what? If this is a system of equations, here's equation 1, equation 2, equation 3. How is that different if that was equation 3, equation 2, equation 1, equation 4? Doesn't matter, it's still the same system. So you can interchange any 2 equations anytime you want to. Doesn't change. That would be an equivalent system. Okay? You might ask yourself, why? Why would I do that? We'll get to that later. Okay? Number 2. Multiply any equation by a non-zero number. Okay? They say constant. Same thing. Okay, a non-zero. Why don't we multiply an equation by 0? Everything goes to 0, you lose all meaning for that equation. Never multiply, and certainly never divide by 0. Okay? Now it says multiply an equation by a non-zero constant. You can also divide, because division is just another form of multiplication. So you could divide by any non-zero constant. You can't divide by 0 ever, so don't ever try, but you could multiply or divide. Because look, if you're dividing by, give me a number, any number. 5. If you're dividing by 5, that's the same as multiplying by 1/5, right? So multiplication, division. So multiply or divide any equation by a non-zero constant. Because an equation, remember, something on this side equals something on that side. You multiply the same thing on both sides or divide the same thing on both sides, not going to change the equation, the meaning of the equation, the significance of the equation at all. Okay? The third thing you can do. Now this one's a little stranger but true. Add a multiple of one equation to another equation. Okay? If you do that, you have an equivalent system. You keep the one that you're multiplying by, so you're doing two things here. Usually, multiplying one equation, adding that to a second equation. That changes the second equation, but you keep the first equation what it was before you multiply it. Okay? That's a new system, but it's an equivalent system. Now that one's a little harder to see why that won't make a difference, but it won't. Take Gauss's word for it. It works. Okay? Now just hitting that because we're going to need it later. Okay, let's go back to our three situations. Now, it was sort of intentional. I did two equations, two unknowns. Okay? But if we were talking about three equations with three unknowns, or 17 equations with 14 unknowns, or whatever, all you're doing is adding dimensions, okay? Like three equations, three unknowns, if they're all linear equations, one line is going here, one line is going there, one line is going there. They're still straight lines, they're just not on the plane. They're in space. If you have 4 dimensions, I can't visualize that because I can't see anymore, imagine anymore the 3 dimensions, but you're in 4 space. So whatever that is, you've still got straight lines, okay? So let's go back to this so I can visualize this pretty easily. What were our 3 conditions of 2 equations, 2 unknowns? What was the first one? Say again? Intersection. 2 lines intersect, one and only 1 point. There's 2 things we can say about that system of equations. It's consistent. What does consistent mean? It has at least one solution. It has exactly one solution, but it's a consistent system. The second thing we can say about that system is that those 2 equations are independent of each other. You may not know what that means yet, but we'll get there. Just get that in mind. If they intersect at all, they're consistent system of equations, and the 2 equations, if they intersect at only 1 point, they're independent of each other. Basically, in 2 spaces, it means they have different flows. We won't go there yet. Okay. What was the second possibility we had of those 2 lines? Okay. Parallel but not intersecting. What can you tell me there? Inconsistent. They don't have a solution. So that's an inconsistent system. You cannot get a solution out of it because they never intersect. Now they are independent of each other. They're not dependent, but they're inconsistent. And what was the third case? They're on top of each other. What can you tell me about those? You have a solution? You have an infinite number of solutions. You know, tons of solutions. Okay, so they are consistent, but they're dependent. They're not independent of each other. They're multiples of each other. Okay, so that means they're not dependent. I mean, they are dependent, They are consistent. So you have two classes, consistent, inconsistent, dependent, independent. One and only one solution, consistent, independent. No solutions, inconsistent, but independent. Say again? Yeah, in two space they are. Three space, it gets a little more complicated than that, but it's still, they are dependent on each other. That's if they line up, okay? And then, so, every condition has some combination of those characteristics. The systems are either consistent or inconsistent. The equations are either dependent or dependent, depending on which one they are. Okay. I'm hitting this 1.1 very quickly, and that's it. Okay. You want to do some exercises in 1.1. Okay, let me tell you this. I'll say it now. I'll try to say it other times as well. Your exercises are at the end of each section. And you notice here the brown, on my book is brown and yours it is. When it says 1.1 exercise. Okay. When I'm giving you assignments, I'm not going to assign you anything here, but you can do something if you want to. I suggest you do odd number. Okay? Let's just take this for an example. I'm not giving any of these. I would say do any of the odds 1 through 5. I'm not assigning these, but if you were going to do them. Okay? Why do I say any of them? If you find this really easy, you do the hardest one in there, you can do it with no sweat, move on to the next section. Why waste your time doing over and over and over something you already know? Okay? Why do I say odd? 2 reasons. One reason, odd answers are in the back of the book. Okay? Now, I've got an instructor's edition. Well, okay. I don't know if all of you have this or not, but I have a few that have not many, just very rare. Well, I haven't even. I see 2 that on this whole page that have 2. So the odd answers are in the back. So that's one reason I assign odd, or I suggest you do odd. But there's a second reason. So what if you do the assignment, odd number exercise, you look in the back, you don't have the right answer, you go back, recheck, you do all you can't figure out why you don't have the right answer. You have to wait until we come back to class and ask me a question. You can do that, but guess what? In this book, this author, Ryan Larson, one of the better authors I've run across, look at the top here, where it says 1.1 exercise, see www.calcchat.com for worked out solutions to odd numbered exercises. So if you can't get the answer in the back, you can't figure out a way to get the answer in the back, then go to calcchat.com. You don't have to wait till the next class. Go there. Free website. Go to calcchat.com and see the worked out solution. If you still can't understand how they did that, why they did that, who would have thought of doing that, ask me in class. But you have 2 things to do if you can't get it. Okay? Look at the answer in the back. If you can't figure that out, go to calcchat.com. If that's still not clear to you, ask me in class. Okay? So you can do any of those odds that you want to using those tools. I'm not going to assign them, but you can do it. 1.2 is now where we introduce the concept of matrices, and that's what we're talking about in this course. This linear algebra is basically a study of matrices and things you can do with matrices, and plenty of other stuff as well, but we start with matrices. And 1.2 begins that. Let's start with the definition of a matrix. Okay? Okay. Okay. Now, I told you about Gauss and told you about Gaussian elimination. I didn't tell you how we did that. We're going to do it with matrices. I figured, why do it with equations, then with matrices? We'll do it with matrices. But it says section 1.1 introduced Gaussian elimination. I didn't tell you how to do that. as a procedure for solving a system of linear equations. In this section, you'll study this procedure, same thing, more thoroughly, beginning with some definitions. The first is a definition of a matrix. Here's what it is. If M and N are positive integers, in other words, whole numbers, no, natural numbers, counting numbers. Why could I not say whole numbers? Whole numbers includes the number 0. We're not using 0. Only positive integers. Counting numbers, 1, 2, 3, 4, 5. Natural numbers, 1, 2, 3, 4, 5. Yeah, okay? And higher and higher and higher. Okay? Those are your positive integers. Okay? If M and N are positive integers, then you can come up with and let me get the thing right, M by N, okay, that's how we write it that way. We say M by N matrix, okay, and it is a rectangular array, okay, a rectangular array of numbers. The numbers in the rectangular array don't have to be integers. M by N have to be positive integers. What do we mean by that? Well, and this is a standard way to do it. A11, A12, A13, A14, dot, 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 up to and including A1N. N is some number, in this case something greater than 4. Doesn't have to be, we could have stopped sooner. Okay? We're going to call this row 1. Okay, row 1, the first subscript for your A's there indicate what row you're in. That's row 1. Row 2 will be A, guess what the first entry is? 2, 1, A22, A23, A24, dot, 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 up to, guess what the last one is? A2N. Okay, now you see what's forming here? You have columns. Here's your column 1. Here's column 2. Column 3. This is column N. Okay? So the second subscript for those numbers is your column number. First subscript is your row number. Second subscript is your column number. And guess how many rows are going to come? You'll have a 3-1, a 3-2, a 3-3, a 3-4, dot, 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 up to a, what's that last one? 3N. I'm not going to write all these. I'm just going dot, dot, dot. What you reckon the next is going to be? A M1, a M2, a M3, a M4, dot, 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 to what you reckon that last one is? A sub M N. This is your row M. Okay? So, what we have, and by the way, you can dot, dot, dots all these other things. Dot, 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 dot. I mean, dots everywhere. Okay. Now, this is a rectangular array. It has M rows. That's what we mean by M by N. You can't have 1.5 rows. You can't have a fractional number, a mixed number. You can't have a negative number. You can't have -4 rows. No, there's no such thing. It has to be positive integers. It can't be 0. You can't have an array with 0 rows. There's nothing there, okay? So it has to be M rows, N columns. To be a rectangle, you have to have, it's not the same number, but all the rows have the same number of entries. All the columns have the same number of entries. Those are the number of rows. So that's your rectangular array. That's what we call a matrix. Okay. Now, I'm going to jump ahead a little bit. Typically, we would name this matrix by a capital letter, and let me tell you what that would probably be. Matrix A, okay? Why? Because we've named all the elements in that little a. And that's usually the convention we'll use. If it's matrix M, we wouldn't use that because we use M by N. Matrix P, then it'd be piece of 1, 1, piece of 2, 2, piece of 3, 3. Yeah, that's usually how we name it. So this will be matrix A. Now sometimes for A, if we want to designate it, we'll put MN. That means it has M rows, N columns. Okay? So we could do that. You could say M by N, but quite often we just shorten it MN. So all these entries here can be any real number. The M and N are only positive integers, but the entries, the A's, any real number. Pi thirds, e to the 5th, square root of 14 over 2. Whatever your entry is, any real number. It could be 7, it could be 3, it could be -5. Okay? Positive, negative, fraction, decimal, those A's can be any real number. The M and N's are only positive integers. Make sense? Now, most of the time when we list it like this, we will put it inside angle brackets. That's how you know it's a matrix. Okay? So there's your matrix. We call each one of these an entry to the matrix. Okay? Now we name one. This one would be named A sub 3, 2. If we're talking about any old one of them, it would be A sub ij, where I is some number between 1 and M, and j is some number between 1 and n, because you're picking out these to be varied. AMN is only that one here, but ij can vary between 1, I varies between 1 and m, and j varies between 1 and n. So you can name any old entry aij, and you pick a value for I and 1 for j, and you know exactly which entry you're talking about. Okay? I think we beat that to death, did we? Any questions about definition of a matrix? Okay. The index I is called the row subscript. The index J is called the column subscript. Now, second. Okay. The I is the row subscript. See, these are subscripts. They're written a little bit lower. Subscript. And the J is called the column subscript. That identifies where you are in the matrix. Mth row, or ith row, jth column. Okay. Now, we call it a rectangular array because every row and every column has the same number. Okay. Every row has the same number of entries of every other row. Every column has the same number of entries of every column. The m and the n may be different numbers, but that's always going to make a rectangle. If m is greater than n, it's going to be deep this way, but shallower, not as long. If n is greater than m, it's going to be longer this way and shorter that way. But it's always going to be a rectangle. Now, I can almost imagine some of you are wondering, what if m is equal to n? What do we call that? If the length is equal to the width, what do we call that rectangle? A square. So we would call this a square matrix. Okay? And we say it's square of order n. For some reason, they like n better than m. So you say usually say n by n, not n. You could say n. But usually, if you see this, a sub n, guess what? That implies it's a square matrix. It only has one subscript. That means that the entries still have two subscripts, but they all only go to n. It's a square matrix of order n. Okay. Now, if you had a square matrix of order n, let's just take a portion of this one. That's the square matrix, right? 3 rows, 3 columns. These entries right here have a special meaning. Okay? Here. Subscripts are the same on all of them. We call that the main diagonal. This one here has no special meaning. It's a diagonal, but it's not the main diagonal. The main diagonal, these are it's A sub II or A sub JJ, okay? They have the same value for both of those. And that's called the main diagonal of a square matrix, okay? So, let's do example 1 real quickly. Super easy. Okay? You come up with a matrix that is a 1 by 1 matrix. 2, okay, that's the one in the book too. There's a 1 by 1 matrix. Okay? Usually we don't refer to that as a matrix, we call it a number. But it could be referred to as a 1 by 1 matrix. Okay? That could be the square root of 2. It could be negative 2/3. It could be any entry, any real number, only one of them, it's a 1 by 1 matrix. Come up with a matrix that's size 2 by 2. Say again? 2 and 3, is that what you said? Okay, 2, 3, 4, 5. All right, he's real creative. Okay, yeah. Okay, 2, 3, 4, 5 is a 2 by 2 matrix. Now, the one they picked out that was a 2 by 2 matrix looks a little suspicious to me. It's 0, 0, 0, 0. That is a 2 by 2 matrix, but that is a 2 by 2 matrix that we have a special name for. It's the 0 2 by 2 matrix. All the entries are zeros. It's certainly still a matrix, but every entry is a 0, so it's a 0 2 by 2 matrix. Okay? We'll run into those later. Okay? How about a 2 by 3 matrix? Give me some entries that could be a 2 by 3 matrix. Second, any number, exactly. Second, did you say 2/3? 1, 2, 3, is that what you, I couldn't hear, my hearing's bad. Is that what you said? Okay, 1, 2, 3. 1, 2, 3, is that a 2 by 3 matrix? Not yet. What more do we need? Say again? You said 0 pi? What'd you say? 0, 5 what? 6? 4, okay. I just can't hear. That sure enough is a 2 by 2 matrix. 2 rows, 3 columns, that works. Look at the one they chose. I sort of did something like this before. E2 negative 7 pi root 2 4. Okay? Now, I can see a little bit why they did that. Now, 5 out of the 6 of these entries are positive. They could all be negative, right? Could any number be positive or negative? I think they cheated negatives a little bit. They didn't have any fractional forms in here. You could have, this could have been 2/3 or 4/5 or negative 7/8, you know, anything like that would work. Or negative 7/5, yeah, that would work. But they also have irrational numbers, e, pi, and square root of 2. You could have had negative square root of 2 or negative e, or pi squared, or negative pi squared. I mean, you could put any real number in the world in there. Say again? Oh no, don't tell me. We were just beginning to have fun. No, we always have fun. Okay. All right. So we'll begin next time with the concept of augmented matrix. Now let's see if I can come up with a few homework exercises for you here. This is pretty easy stuff. I want you to do any of the odds 1 through 3. This is on page 22, exercise set 1.2. And we'll stop there. And you can do any of the odd numbers you want to in section 1.1. Okay? 1 through 5. Yeah. They're really easy. I apologize ahead of time for them being way too easy, but get over it. Okay. All right. And we'll pick up. Where did I pick? Oh. Okay. That's what we'll pick up next time. Okay. And we'll really get into math next time and won't have any other distracting things to do.